Assalamualaikum and good day. Today our group will presenting about lead and lag compensator. A lead compensator and a lag compensator are two common types of controller used in control system to improve the performance and stability of a system. This assignment taught us how to utilize Scilab and how to calculate lead and lag compensators. It also demonstrates how to extract the calculations result and output from the graph in Scilab.
Okay, for question 1, which we have to create 1k, 2 poles and 3 zeros, which is our group have decided to take the value k, which is 1, 0, 5 and 10, poles 0, -5 and -10, which is our system is stable because value of the 0 is smaller than the value of the pole.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Azizam bin Kamaruddin. Okay, for my part is to explain the question 2 based on the equation that has been created from previous question. With using Scilab, it produces box plot and a figure where the first graph is amplitude response and the second graph is phase response. It also produces the value of gain margin, phase crossover frequency, phase margin and phase crossover frequency. For the gain margin that has been produced from the Scilab is 8.9672122 decibel. The next one is the value of phase crossover frequency that is equal to 0.4468695 decibel. Okay, for the next one, we move to the value of phase margin that equal to 55.95 degree. And the last one is gain crossover frequency, which is equal to 0.159.549 decibel. For the question 3 about lead compensator, which is required further improve 10% of current phase margin of the response. Before that, let's we describe about lead compensator first. A lead compensator is an electrical circuit that when provided with a sinusoidal input generates a sinusoidal signal as output with a phase lead in comparison to that of the applied sinusoidal signal. It is also known as lead network. To find the new phase margin or new PM, the previous phase margin that produced from question 2 need to multiply with 110%. Then, don't forget to plus 15 degree as the value of safety margin for lead compensator. After that, it need to find the value of alpha, omega and tau to create a new general solution as shown in the box figure. After get the new general solution, put all the new equation into the coding to produce new amplitude response and phase response. We can see the result of amplitude response at the first graph and the phase response result at the second graph. For the next step is to make sure the result of the new phase margin is better than 45 degree and the required results that display in Scilab is 179.99686 degree, which is more than 45 degree. Thus, it is satisfy the requirement too. Finally, to confirm our ramp response, it need to plot the value of x that equal to 0.048 at x-axis and y-axis. After that, find the value of steady state error, which is equal to 0.047. Thus, the value of steady state error is less than 0.05, which is satisfy the first requirement.
A lag compensator primarily used to improve the steady state accuracy and error in a control system. As you can see here, this is the coding we load into the Scilab to get the phase margin. For the calculation part, our new phase margin is need to make 55.95 times 100 and tens per 100 and get the answer is 61.545. 61.545 need to plus with 5 because of the safety margin for lag compensator, and we get 66.545. And then negative 113.455. The new gain crossover frequency or phase margin is 0.1434 Hz or 0.9 radian per second. Using Scilab, gain at omega c is 7.082 dB equal to 20 log A. From the equation, we get alpha equal to 2.26. To confirm phase margin is more than 45 degree, the overall phase system margin is 68.3184 degree, which is more than 45 degree and satisfied the requirement too. To confirm RAM response, steady state error is 0.049 minus 0 and get the answer is 0.049, which is less than 0.05. Thus, satisfied the first requirement. That's all for my part, and thank you.
Okay, for question 5, based on question 3, which is lead compensator, and question 4, which is lag compensator. Lag compensator can be used to improve phase margin by 10% because the phase margin for the lag compensator has the bigger value compared to the phase margin for lead compensator, and achieve 10% improvement of phase margin, which is the phase margin for lead compensator question 3 is 61.545, and for lag compensator, which is question 4, is 664.545. Okay, comparing the phase margin value for question 3, which is 20.595, and question 4, negative 113.455, it is clear that the phase margin for question 4 is significantly higher. Therefore, the lead compensator in question 3 did not achieve a 10% improvement in a phase margin. A lead compensator does consist of a dominant zero and a pole, and it is designed to increase the phase margin and stability of a system. It does this by adding a positive phase to the system. However, it does not directly enhance damping or reduce overshoot, rise time, or settling time. These factors are influenced by other aspects of the system design. A lead compensator can increase the system's bandwidth, which might contribute to a faster response. It is important to remember that expanding the bandwidth can also bring up difficulties like increased noise and amplified high-frequency disturbance. On the other hand, a lag compensator reduces the gain at lower frequencies and increases the system negative phase. This can result in a small bandwidth and smaller response. However, it can also increase stability and decrease overshoot. And lastly, in conclusion, based on the phase margin value provided, it seems that the compensator in question 3 did not achieve the desired 10% improvement